Hello, my name is James Carl, and this is Lab 5, where I will be discovering slinky physics. This lab was given to me by the professors, and it consists of one man dropping the top of an extended slinky and watching the movement of the slinky from the top and watching the movement of the slinky from the bottom. We discovered that the bottom of the slinky does not move whatsoever. The reason behind this is that the force of the spring acting on itself counteracts the force of the gravity caused by the Earth, which means that the bottom of the slinky does not move until the top of the slinky hits the bottom of the slinky. Here is the video I used to track the data. As you can see, the bottom of the slinky does not move until it makes contact with the top of the slinky. The reason behind this is that the bottom does not feel the effects of gravity because the top of the slinky has a spring force that is counteracting it until the bottom and top meet. This lab contains Newton's second law, just as the last one that involved a spring. The spring can be thought of as two different parts: the top of the slinky, where F net equals gravity, and the bottom of the slinky, where F net equals 0. The bottom of the slinky does not equal gravity until the two ends meet. The spring force is also a big part of why this does what it does, because it is used to calculate the effect of the spring on itself, counteract the force of gravity. First, I put the video into Tracker and used two different point mass systems. The red one followed the top of the slinky, whereas the bottom one followed the movement of the bottom part of the slinky. You can see where the axis is, and you can see it is obviously going negative. Once all of the data was tracked, I went to my t versus y graph to see the motion of the top of the slinky. As you can see, it is a constant speed as it falls, even when the masses become 1. The next graph on this page is my t versus y graph for the bottom of the slinky. As you can see from the top, the slinky does not move whatsoever while the slinky is falling, but once the top reaches the bottom of the slinky, it starts to move because it feels the effects of gravity finally. The reason why the graph looks so funny is because for every time interval that Tracker wanted a point for the first part of the graph and needed one for the second, and the frames were not quite correct. You can tell by the jagged line. You can just think of this as a straight line in the negative direction. This lab relied heavily on the code from previous labs, especially Lab 4. There were only a few fundamental things that needed to change in order to receive my data and model it correctly. These are the initial conditions. For the Python code to work, I had to place a ball in the code to give the spring something to attach to, otherwise I couldn't figure it out. But I gave the ball a mass of 0.402, the spring a mass of 0.1, and the position of 0.03, negative 0.7, and 0. The timestamp I put on this was a little bit shorter than the earlier one, which was 1 divided by 350, because it showed the speed of the slinky well, and gravity, as always, equals negative 9.8 meters per second squared. The constants regarding the spring are exactly the same as last lab, as you can see them at the bottom of the screen. Now I will show you what this model looks like when my code is run. You can see there's a black ceiling, or such, that the spring is attached to, but when released, it drops lower and lower until it hits the spring, then falls at the speed determined by gravity. In conclusion, the slinky mystery is not really a mystery, but just another physics problem. In this case, the force of the slinky on itself, when released, is strong enough to hold up the bottom as it falls.